Welcome to the Insightful Professor. In today's discussion, we're going to continue our examination of defining classes in Java. A little bit of a refresher before we get into some new material. When an object is created from a class, we say that that object is said to be instantiated from the class. It's an instance of the class. But exactly what does that object consist of? Well, when we define the class, we define what are called instance variables, and we also define methods. Remember, the instance variables define the data content or the structure of an object or an instance of the class, and the methods define behavior or operational aspects, how we're going to interact with that structure. So each object, when it's instantiated, has its own copy of the member variables, or what we call the instance variables. So that means that if we define a class and the class says, hey, you have an x, which is an integer, and you have a y, which is an integer, and these are two instance variables, then if we declare an object which is an instance of that class, that object gets its own x and y. If we then instantiate another object from the same class, that object gets its own x and y, distinct from the x and y variables that exist for the first object. So that's why they're called instance variables. So the member variables of one object are separate and distinct from those that have been created or allocated for another instance of the class, another object of the class. So when we work with these variables, we're typically, through the idea of encapsulation and supporting what's called data hiding, going to access these variables not directly, but by going through what we call the interface, the public methods. So we have, in particular, accessor functions that are going to allow us to take a look at or get the values of these attributes by making calls to these methods. And remember, that's done by sending messages to the object. So when an accessor function is called for an object, it will return the value based upon what value or values currently exist within the instance variables of the object that provides the context to make the call. That is, we call this the calling object. So remember, when we created something with scanner, we maybe created something called input or keyboard. And input or keyboard would be the name of the reference variable associated with the scanner object. We then used input or keyboard, whatever name we gave to the reference variable, to qualify the call to methods such as nextInt or nextLine. That's what we're talking about here. We would be invoking such a function or method using a reference variable to qualify the call, to say which object is making the call or which object is involved in the invocation of the function. So an instance method typically interacts with the instance variables, or what it could do is, instead of just retrieving the value, what it could do is it could calculate values based upon what's stored in those fields. So remember, rather than storing something that is a derived value, which could become stale, what we do is we calculate it on demand. But in any event, these instant methods or functions will be interacting with the instance variables and the values that they contain. So the instance methods require then, obviously, that an instance of the class or an object exist in order to qualify the call, such as input dot something or other, or keyboard dot something or other. That is such that those reference variables are making a reference to existing objects that have been instantiated on the class. That may seem obvious if you're comfortable with the material that we've covered in the past. But let's go ahead and talk about something a little bit different. And we'll talk about what are called static members. But before we do that, again, let's continue with our refresher. So here we have an example of a class called widget. And widget has two variables defined. These are both designated as private because, remember, we're doing the data hiding or the information hiding. We're not going to allow direct access from code outside the object or outside the class to touch these variables, but we have to go through the interface. So we define double as the data type of price, and we define int as the data type of quantity. These are both said to be instance variables because when we create an object of type widget, each object or each instance is going to have its own copy, its own storage for price and its own value, its own storage for quantity and its own value. So that's, again, why they're called instance variables. So here's the constructor called widget, which accepts something called P and Q. Those names are not important, other than when we're within the code of the constructor, going to make a reference to those names in order to access whatever argument values have been passed to us. Then we take those values and assign them respectively to price and quantity, the two instance variables. So when the object is constructed or instantiated, storage is allocated. We pass a value here for P, some double, which will then get assigned to price, and Q, which is then going to be assigned to quantity, and Q again is an integer. Then later on, we invoke these methods here to access the values. And again, these are designated as public, so we can invoke these from code outside of the object, outside of the class, and then gain access to the values. So that's a quick review, and hopefully all of that is clear to you. So when we create the widget objects, we do it here by using the new operator, invoking the constructor, and then passing a value for P and for Q, for the price and the quantity. And then we see how that got assigned by examining the code of the constructor. Later on, we invoke the accessors, and here's what we get back. So to look at this exact code, if you want to see it in detail, we have widget.java and useWidget.java. Widget.java is the class, and useWidget.java is the application that utilizes the class. I'm going to quickly show you that as part of our review. Okay, so here I have the class widget, and here's the exact code that we saw. So when this gets defined, we will compile this, although this itself is not executed, but does contain the executable code for the member methods. So that's the widget class. Then we have useWidget, and useWidget is going to use the widget class and create objects of type widget. And we'll have W1 as a reference variable, W2 as a reference variable. And again, this is just piecing together the concept that we just presented in the review. To show you how this works, I'll go ahead and compile and run the code. Again, I'm running the application because this thing called useWidget has a main method. So we'll fire it up, and here we go. We see the system out print line showing you what's in quantity and price for widget 1. Here's the output. Then we see the system out print line calls showing us what's in quantity and price for widget 2. And we see the result down here. And take a quick look at that and just make sure you're comfortable with it. And that completes our review. Now we're going to get ready to look at the new stuff. Okay, as we talk about the classes and their member variables, we were talking about instance variables or instance methods. But there's another thing here where we can define the fields or the attributes or the variables which are not part of each object or each instance, but are owned effectively by the class. These are called static members. So we have static fields and static methods, so that when we create an object, regardless of how many object instances we instantiate, there will be only one instance of a static field, whatever that field is, and only one instance of the static method. But more importantly, we're talking about fields at the moment. We'll talk about the static methods in just a bit. But with the static fields, what happens is storage is allocated one time regardless of the number of instances of the class that exist. In fact, storage gets allocated even if we don't create any instances of the class. You don't make any objects, the storage is still available. So they're pretty neat and we'll show you how they work and why we would use them. And there's something you're already familiar with that falls into this category. We'll show you what that is. So to invoke a static method, you use not so much an object reference variable, although that's a possibility, as you would use the name of the class. So you use the class name to qualify the call to the method, or say the reference to the field. And here's one that you're familiar with, the good old math class. Remember, math has all kinds of neat functions such as square root and absolute value and trigonometric functions. And what we're doing here is we're invoking not an object reference variable dot some method, but we're invoking the class name and then the method. But this is a static method, okay? The idea is the static method is accessible without instantiating an object. Or if we choose to invoke it from within an object of the class, then we don't qualify it with an object reference variable. We qualify it with the name of the class. Okay. Now, if you think about where these guys come from and how we use them, we're going to be using things like square root, absolute value, and all of these other real nice math functions in a variety of different programs. So many programming languages will provide libraries with these subroutines, and then we can invoke them. Or they may be built in or inherent within the compiler, the core language itself. But with Java, what we see is we can effectively extend the language by defining all of these functions that we're interested in invoking from any code and create them within a class and make them static. Then we simply invoke the function by qualifying the call with the name of the class. And we basically added functionality to the language by adding this other collection of subroutines. That's effectively what math does. Turns out we would probably never create a math object. It doesn't really make any sense. It's not necessary, because what we're doing is we're simply using this as a collection of subroutines. In addition, there's some other stuff in there that we'll see shortly. Those are also static members. So static members, what are they? A member variable or member function can be created such that it does not belong to any specific instance of a class, but can be thought of as the property of the class itself. These are referred to as static members. We can have static member variables, static member functions, or member methods. If a member variable is declared as static, then all objects will have access to it. In fact, it's not stored within the object, but it's stored once within the runtime memory where the class becomes available to all code that's executing in that current environment. So if a member function is declared static, it can be called before any instances of the class are defined, or even if no instances are ever going to be defined. That's what square root was from the math class. It's a static member function. So a static member function can only act upon or operate on static member variables, cannot operate on instance variables. And that makes sense because the code itself lives outside of any instances and doesn't require an instance to exist. So therefore, it's kind of independent of the objects or instances that get instantiated from the class, if any do. So therefore, the idea of accessing the instance variables doesn't really make any sense. Okay, the static fields. How do you define a static field? Simply use the keyword static. That's the key to getting this going. You simply say static after the access specifier and before the data type here. So we're going to say private static int and then some variable. And this, by the way, is how we initialize it. When it gets declared within the class definition, if we do an assignment statement like this, this will cause the instance variable to be populated with an initial value. If we don't assign it, a value, then it will be initialized with the appropriate default value for whatever the data type is. And for int, that data type happens to be 0. So this was not really necessary to do this assignment, but it's good practice to make it explicit that you are assigning an initial value rather than accept whatever the default might be. Remember, if we had double or floating point, then this would be 0.0. And if we had, say, something like a reference variable, it's going to be a null pointer. But here, it's best to initialize it to something explicitly so that we're sure what's done. It kind of provides documentation for that initialization. Okay, here we have static methods discussed, and they're going to be illustrated in a couple examples that I mentioned at the bottom of the display here, metric.java and metricdemo.java. The methods can be declared static just as we would declare the variables as static. Simply use the static keyword, which is exactly what we did here. So we say public static double, that's the return type, the name of the function or the method, in this case miles to kilometers, and then the argument, and then the body of the code, whatever that would be. Now, when a class contains a static method, as we said before, and we're obviously reiterating this point, is that it's not necessary to instantiate an object in order to use this code. So here we're invoking through the metric class this static member function called miles to kilometers, and we're passing it a value of 1.0. Okay, and that points back to what we were doing up here. And okay, that's going to do its thing. It's going to return a double, and that's what we're returning here, something of type double, storing it in this variable. Very similar to what we've done with the math class. Here's where we're invoking the random function or constructor to generate a random number or a series of random numbers from the math class. So that's pretty neat. Okay, so we're familiar with some of this already. We've used it, but not really formally described it. So now we see that this is really what math is built upon. It's built upon a bunch of static members. And these members can be functions. The members could be class or static variables, or constants, as we'll see as well in a moment. And we're going to be able to build our own. So let's take a quick look at metric Java and metric demo Java, because those are examples of actually building our own. Okay, so let's get rid of these guys and go and look at metric and metric demo. So here's the metric class, and what we have is a definition here of miles to kilometers, which is accepting a double and returning a double, but notice it is static. And we've got our Java doc comments up here with the tags for parameter and return. So you can take a quick look at that, make sure that's clear to you. Likewise, we create or declare kilometer to miles going in the opposite direction, which accepts a double, returns a double, and likewise it is static. So we then go ahead and use this within our metric demo. And what we're doing here is declaring some variables. We're going to be using scanner to get some input from the user. And then what we're going to do is take the value that the user enters, put it into this variable called miles, pass that as an argument to metric dot miles to kilometers, metric being the class, mile to kilometers being the static function. That will return a double, which will be the kilometers, and then we'll display the information. And then we'll make a call in the other direction as well. So let's go ahead and fire this up and just show you how it works. So we'll enter something simple like 100 miles, and it comes back and tells me 100 miles is equal to 160.9 kilometers. So let's see if it works the other way. Let's try 160.9. That's the number of kilometers, and it converts it back quite nicely to 100 miles. Okay, and that's the basic operation of these and laying the groundwork for how these get used. Let's go and talk a little bit more about this, and we'll go back and kind of tweak this guy back here. We'll refine this metric class just a bit. Okay, constants. What are constants? Constants are effectively defined very similar to the idea of being a variable, except what happens is we add the word final. This is what makes them constant. So you would have an identifier that is of a certain data type, and you assign it some value, just like declaring a variable and initializing it, except this is the only time you're going to get to assign it. It's the final assignment. So by adding the word final, this makes it a constant, more appropriately perhaps a constant identifier, because clearly 1.609 is a constant value. But here we're associating that value with this identifier. And remember again, our naming convention or our naming standard says we're going to put this all in uppercase to emphasize the fact that this is a constant identifier or a named constant. And again, we're working with the notion of static. By making it static, it becomes what is called a class constant. Rather than stored within an instance or an object of the type, it is stored within the class as a whole and accessible or shared by all methods within the class. So what we're doing is adding that static keyword. So we declare a class constant. It gives a single image of this thing, excuse me, whatever it is. And that single image is available to all methods, all code within the class. And again, the emphasis here is we must use static. Now this is more efficient than creating it without the word static. If we created it without the word static, it would be an instance constant, which means if I create 10 objects on the class, there would be 10 instances of this constant, one stored in each of the objects that got instantiated. But by making it a class constant, which we achieve by calling it static, there is only one version of this thing, one image of it, one block of storage, so it's more efficient. Technically, it's not incorrect to make it an instance constant, but this makes more sense. It's more efficient, and again, it's going to be shared by all. So we don't really need to make instances of it. Now, another concept that comes up, excuse me, is the notion of making such a constant public. Does that make sense? If it's a constant, it's going to be used within the code for the member methods. So why would we want to expose it by making it public? Why not just keep it private? Well, think about the math class. The math class really is such that we may declare some things that we want people to know about who are using the class. So people and code that lives outside the math class, we want to be able to share some of the inner workings, not just functionally by giving access to methods, but how about good old pi? Pi is something that we use quite a bit, and pi is defined as a named constant or constant identifier within the math class. And in order to make it available to those static member methods, but also make it available to us if we need to know what pi is and use pi without defining it ourselves, then what we simply do is we say math.pi, but of course, to be able to do that, it has to be static. So this is where we would have a static constant. If we made it private, we couldn't even see it, and it would be kind of a moot point. But by making it public, we can gain access to math.pi, and furthermore, we gain access to it by using the class name of math, rather than having to instantiate an object. So that does make sense in certain situations to have these public constant identifiers. Okay, that's pretty much what I want to say, but now let's go back and refine our example where we were looking at metric. As we looked at metric, one thing that we didn't do was we didn't create a named identifier. We left it here as a constant introduced in here. Suppose there was a higher degree of accuracy and we wanted to change it. Maybe it was like 1.6089 something or other, and we wanted to carry out to more digits. Then we'd have to change it in every one of the methods that we have here, because we have replicated values or duplicated values. So it would make sense to make this a constant identifier. Now, if we declared it as a constant identifier within miles to kilometer, it would be local to that method, and we'd have to do the same exact thing down here. But if we declare 1.609 as a constant identifier or named constant within the class, then it's accessible to all of the methods. So let's see if we can give that a try here. Let's go ahead and say what we're going to do is say, we'll call it public static, and what we do is, remember, we're going to say the data type, but we're also going to inject that word of final. We would say public static, then we add the word final. This is what's shown on page 9, and then we would say double, and we would do something like kilo per mile equals 1.609, and we define that identifier here. Now we can take that identifier and replace that literal value in each of our calls. Okay, that would give us access to it. But also by making it public and static, we can gain access to this on our own outside. So let's go ahead and compile the code, and just note once again there's a little asterisk up here saying this has been modified, needs to be compiled. So with this IDE, I'm going to go ahead and say Control S, compiles the code. Now I'm going to go back here, and here's where we have the metric demo, and the metric demo has not been modified. I'm going to run it now, which is going to invoke the code in that class where I have modified the class, and as I do this, let's see what we get. So let's go ahead and fire this up. I'll enter the value of 100 as we did before, and I get 160.9, and I put 160.9 for the kilometers, and I get the 100 miles. So it worked fine. So making the modification here of removing the literal value but using this named identifier, this named constant identifier, worked great. So again, notice it's defined within the class, so it's available to all of the methods. It's kind of global in that sense. But another neat thing about this is we can use this identifier, right, kilo per mile, and if for some reason we wanted to see it from outside, we could put a message in here, such as this, that says system.out.println, and then we could put something like the constant identifier value, and go ahead and add the name of the class, metric, dot, and then the name of the guy here of kilo per mile, which is exactly what we want. Fire this up, compile it, and run it. We'll do the 100, and then we'll do the 160.9, and then at the end, here's where we actually accessed that named constant identifier, because it was static, from code outside of the object. And again, the instruction that did that was simply making a reference to metric.kilo per mile. And that concludes my presentation of this little enhancement to classes using static members. I hope you found it useful, and if you want to offer any comments, please do so in the section below. And once again, thanks for watching.